Good morning and welcome to section 3.2 of nonlinear models. And today we're going to talk about where our models for a differential equation is going to be nonlinear. And so we're going to talk about population dynamics. And we saw that the exponential growth model, which we've dealt with in 1.3, and last section we had dp over dt is equal to kp when the rate of growth was proportional to the number in the population. Well, in this model, the relative growth defined by dp over dt over p equals k is a constant. This model is not realistic because of the limited resources of the environment. For other models, the relative growth rate can be expected to decrease as the population increases in size, so reaching a carrying capacity. The assumption that the rate at which a population grows or decreases is dependent only on the number p present at, and not on any time-dependent mechanisms can be stated as such. dp over dt over p is equal to f of p, or dp over dt is equal to p times f of p. This differential equation is rarely assumed in models of animal population and is called the density-dependent hypothesis. So for the logistics equation, which is what we're working with, this is mainly the differential equation that we're going to be working with, and we're going to find the solution of this. And suppose an environment cannot have more than a fixed number of individuals, k, in its population. K is a carrying capacity of the environment. So f of k is equal to 0, and let f of 0 equal r. Assuming that f of p is linear, we get f of p is equal to c sub 1p plus c sub 2. So now let's go ahead and solve for f of 0 equals r. And then we'll also do f of k equals 0. So substituting in, if f of 0 equals r, then we can say that r is equal to c sub 1 p plus c sub 2, where p is 0. So plugging in, that's real easy. We found what our r is. R is equal to c sub 2. If we plug in f of k equals 0, now we have 0 is equal to c sub 1 times k plus our c sub 2, which is now going to be r. Solve for c sub 1, we're going to subtract r to both sides. Get c sub 1 k, divide both sides by k, and our c sub 1 is equal to negative r over k. So now we solve for c sub 1, c sub 2. So our equation for f of p is equal to, instead of saying c sub 1, we can say, you know what, I'm going to rewrite this to be c sub 2 plus c sub 1p, just so that we can have the minus sign as our operation in the middle. So we'll have c sub 2, which is r, minus r over k times p. And so that's f of p. Now, if we're going to have the differential equation, our differential equation is dp over dt. And then as you saw up here, it could be divided by p, or we can multiply that by f of p. So then I'll just multiply the right-hand side by f of p. And so what I'm going to get would be dp over dt is equal to p times r minus r over kp. Now, we can do another substitution where we can just write this a little bit better, where we can say, okay, well, let's make a equal r, and let's make b equal r over k. If we do that, then this is what we could write for our differential. dp over dt is equal to p, and then a minus bp. And so we have the equation written just a little bit differently, a little bit cleaner, by using a substitution of a and b. So that's our logistic equation. So the logistic equation, its solution is called the logistics function. The logistic models are not very accurate when the population is large. So what we're going to do is we're going to find the logistic function, and this is a good model, except for again when the population is going to be relatively large. And so what we're going to do next section is we're going to actually solve this differential equation.